All right, you're gonna need your calculator today. We have two more sections to cover, two more topics, really three topics. We have antiderivatives, Newton's method, and differential equations. Dealing with differential equations. Today we're going to deal with Newton's method of solving an equation.
Is antiderivative the opposite of the derivative?
Hmm?
Is antiderivative
Yep.
the opposite?
The undoing of the derivative. Everything in the mathematical process world has a way of undoing it, process to undo it. Every process has an undoing process. The antiderivative undoes the derivative. A little bit easier, though, dealing with the antiderivatives. Today we're going to talk about Newton's method of solving equations. We have an equation x cubed minus 7x plus 7, and we have this equal to 0. And we want to solve this equation. We want to find values of x that make this equal to 0. If I take a look, this is also zeros of the function. And also x-intercepts. When you have an equation set equal to 0, we are looking to see if we talk about what equals 0, the zeros of a function, or if I'm looking at graphically, this is your x-intercepts. So you're looking at values that make our function equal to 0. Okay, values of x that we have to make x equal to 0. Well, there's no way of factoring this down. There's not a quadratic formula that we can utilize because we're not in the quadratic form. But we still want to be able to find ways of coming up with the solutions. And Newton was able to develop a way to allow us to solve this type of equation. But what we're going to take a look at here first is let's type in the function into our calculator. Let's just take a look at the graph of this. So we're going to type in x cubed minus 7x plus 7. And if we take a look at the graph of this, oops, thank you. We can see we hit our x-axis at 3 different points here. We hit our x-axis at 3 different points. Now, it's sort of tough to see here, but this actually goes below the axis and back up again. So if I would zoom in, you'll see it go below the axis and back up again. So we have 2 different points here between 2 that would work. And then we have another point that's outside of 2. So if we take a look, we're somewhere between 1 and 2. We can guesstimate and be able to find values of our function by looking at just plugging values in, plugging in and solving and seeing, do I get a value of 0? So let's calculate what is our function value at 1. Well, with our function, with our calculator, we can go second and calculate our value, and we can calculate our value at 1. You get a value of positive 1. And if we take a look at 1.5, what's our value at 1.5 of our function?
Negative 0.125.
Negative 0.125?
Yeah.
At the value of 1, we are at positive 1. At the value of 1, we are at a value of positive 1. At the value of 1.5, we are down here, which tells me if I am positive here and negative here, I have to cross the x-axis somewhere in between those two values, because I go from positive value to a negative value. If I go from positive to negative on an axis, I have to go through 0. So if we try another value, let's try 1.4. If we try 1.4, what's our function value at 1.4?
Negative 0.056.
So we're negative at negative 1 point, or at 1.4 still. The question is, we want to still continue to try values here. Well, if I take a look at my values, am I going to be somewhere between x equals 1 and x equals 1.4, or x equals 1.4 and or 1.4 and x equals 1.5? Which one will be in between?
1 and 1.4.
1 and 1.4 still, because we're still positive here and negative here. So let's try 1.3. What's our function value at 1.3?
0.097.
0.097. And the key there is that is positive. So at 1.4, I'm negative. At 1.3, I'm positive. So somewhere between 1.4 and 1.3, we have to cross the x-axis. So let's try 1.35. Let's go halfway in between. What's our function value at 1.35?
0.10.
Positive?
Yeah, positive.
So we're positive 0.1010. Okay, so which two am I going to be in between? Am I going to be in between 1.35 and 1.4, or 1.35 and 1.3?
1.35 and 1.4.
Somewhere in between here, because we are negative here and we are positive here. So we can try another value. Let's find a function value at 1.37. What's our function value at 1.37?
Negative 0.018.
Negative 0.018. So what two values am I going to be in between? 1.37 and 1.4, or 1.37 and 1.35?
1.35.
Yep. Because this one is negative and this one is positive. So I could try my function value at 1.36. Negative 0.004. So which two am I going to be in between? 1.35 and 1.36. Well, what's the halfway point between 1.35 and 1.36? Well, if this was 50 and this was 60, I can go f at 1.355. Think of it, if I just had a 0 there and a 0 there, I have 50 there, I have 60 there. Halfway in between would be 55.
0.002.
0.002. And it's a positive value. So I could narrow it down now and see this one's positive, this one's negative. I'm somewhere in between 360 and 1.355. So I could go halfway in between them if I wanted to, or I can go 1.358. And the key is we're just looking basically now, is it positive or negative?
Negative 0.001.
Negative 0.001. So I'm somewhere in between these two values. And I can play this game and continue this game until I come out to a value of 0. But as you can see, my values here keep on getting closer and closer to 0. And ultimately, that's what we want to find. Well, we could go through the process time and time again to do this, but it takes a lot of time to be able to do this. We can continue with this process, and it would continue to get closer and closer to it. But once again, you're constantly trying to narrow down between two values. So Sir Fig of Isaac Newton developed a way of being able to solve these equations. And the equation that we just had up there was the first equation that he utilized to solve this. We start talking about a recursive formula that we talked about when we were in pre-calculus at the very end. We need to have an initial guess. We need to have some initial guess. And this is our x1 value. This is our initial guess. What Newton figured out was by utilizing our idea of derivatives, is you can take an initial guess and find the next guess by calculating this initial guess, our function value of this initial guess, divided by the derivative of this initial guess. And once again, we need to have an initial guess. If we sub n1 in and solve for the next value of x that is closer to the actual root, which is going to be x2. Then we sub in n equals 2 and solve for the next value of x that is closer to the root of the equation, which is going to be x3. And we continue this process over and over and over again. You find an initial guess, you substitute it in, you're going to get a second guess. It's going to be closer to the root. You substitute that second guess in, that's going to give you a third guess that's going to be closer to the root, and it will narrow it down. So let's take a look at this. Now the key is, once again, dealing with this formula here, Newton's formula. We're going to substitute x, or we're going to say x1, our initial guess is a value of 1. So we have n is equal to 1, which leads to x1 plus 1 is equal to x1 minus the function value at x1 divided by the value of the derivative at x1. This is for n is equal to 1. If I put 1 in there, I get 1 plus 1, which is 2. Well, for us to be able to utilize this, we need to also work with the derivative. We have our function is x cubed minus 7x plus 7. And we have to find the derivative of this, which hopefully we can say is 3x squared minus 7. So to find x2, this is equal to x1, which we're saying is a value of 1, plus our function value at 1 divided by the derivative at 1. Or our function value at 1 is 1 minus 7 plus 7. 1 minus 7 plus 7, so it gets a value of 1. And the value of the derivative is 3 times 1 squared minus 7. So we have minus 4.
Yep.
So we have 1 minus 1/4. So we have 3/4.
Yep.
Or 0.75. If n is equal to 2, this tells me we have x2 plus 1, n plus 1, is equal to x2 minus my function at x2 divided by my derivative at x2. Now we start running into some calculation issues because this is a little bit more work than the first one there. So we have x2, which is 0.75. I'm sorry, that should be a minus there, shouldn't it? Here we go. I'm sorry. That should be a minus in there, which means this should be a minus here. So we should come down to 1.25. There we go. So we have 1.25 minus our function value 1.25. Now we start having to deal with some issues here. So we have our function value at 1.25 over the value of the derivative of 1.25. Let's go to our calculator. And let's be able to KYC, know our calculator a little bit better. We can easily find our function value 1.75 by, let's see, second calculate 1.75. Try it again, second calculate.
Okay.
Value 1.25, there we go.
Now we have irrational decimals.
Yeah, we start getting into some problems here. So you have 0.201325, okay? And also we have to deal with our derivative. So let's make life easy on ourselves. I'm going to zoom this back out. And let's type into our y2 our derivative. So we have 3x squared minus 7. So we have these two functions in here. And what we have to calculate is we have to calculate a value at our function and a value at our derivative and divide these two values. And we have to subtract off 1.25 from that. So let's see how our calculator can work this. We have y1 and y2. Let's quit out of this. Let's get our 1.25 minus. Now what we want to do is we want to evaluate our functions at 1.25. If we go to our vars button, which is right beside the clear, okay, let's go to our vars button. Your y vars is your y variable. Go to your y variables. Hit your right arrow. Okay, so what we have here is we have function, parametric, polar, on, off. We want this right here. What this gives me is this gives me our y1, y2, y3. Hit y1, hit enter. Now what your calculator will do for you is allow you to put a parenthesis 1.25. What this will do is this will evaluate your y1 function at 1.25. And we have to divide that by, once again, we have to go through the exact same process. Your vars, your y vars, your function, y2 at 1.25. Okay, this will evaluate your derivative at 1.25. And now hit enter. You get 1.337837838. Okay, what I'm going to ask you to do is I'm going to ask you to continue to write these values down. So you're going to have 1.337837838. And you want to write out the entire decimal because we're going to do this until we start repeating.
This can be hard to explain to Preston. Calculator not his friend very much.
Now, we want to then evaluate at this value. Go through the exact same process. So you have now x3 n is equal to 3. So we have, x4 equals x3 minus f at x3 divided by f prime at x3. Well, this x3 is this value that we just calculated here. This is a value that we're going to use our answer button with for right now. So let's take a look. We have to go our answer, our function value evaluated divided by. So if we take a look at what we have here, we have our answer So I'm going to go second at negative sign minus our vars, y vars, function y1, parenthesis, our answer, divided by vars, y vars, function y2, at our answer. And we get 1.35599. What you can see is we had 1.3378. Now we're at 1.3559. Our values are getting closer to each other. Well, let's make life a little bit easier on ourselves. Okay, let's use another function of our calculator, which is a store button. So let's hit the store button, which is right above the on button. Let's store this to X. And hit enter. Now, everything that you have, whenever you use X, it's going to be this value. So what we can do with this is this now go X minus, once again, we have our vars, y vars, and we're going to get easier with this also, at X divided by our vars, y vars, second function at X.
I'm waiting for you to tell us there's the function on the calculator that does it all at once.
It's getting there. Okay, so we hit enter. As you can see, I got 1.35599. Here I got 13568. We're getting closer to the value. Let's now store this to X. Okay, now don't go, just store it to X and clear the next line. We're not going to go through all your y bars. We're going to make it easy on ourselves. Okay, we just stored this to X. I want to utilize this all over again. This X minus y1 of X divided by y2 of X, I want to use that again. So if I hit second enter, I pull this line down. If I hit second and enter again, I pull that line down. Now my X value is this. So I don't have to go through all the y bars. I could just pull this line down again because all I'm dealing with is X. So if I hit enter, I get 1.356895868, which is almost identical to what I have. I'm good up to the 9. Here I had 3655. Here I have 5868. So I'm close. So let's store this to X. So store to X, hit enter. Second answer, second, I'm sorry. Let's clear that. Second enter, second enter. Pulls that line back down again for me. I get 1.356898668. I get the exact same thing, which is as close as we can get to the actual value. Let's make this even easier for us. Because we're always having to pull that answer down or that down. Now, we can always continue to do that, but I have to remember that formula. Let's go to my y equals now. Let's go to my y equals, and let's go to y3. Let's type in what we just had to type in before. X minus y bar, bars and y bars, y1 of x divided by bars, y bars, y2 of x, parentheses. So we just typed in Newton's formula. There is other values. Okay, there's other values. They just, let's zoom out. What is going in here, what's happening now is your y1, y2, y3 are all being graphed. Let me zoom this out. You're going to get all these values here. Okay, I'm just looking at the first one. If I wanted to turn those off, I could turn those off.
Yours is in color though.
Mine's in color.
Yeah, that helps.
If you don't want that other garbage there, and that's fine. If we go to your y equals, turn off by highlighting the equal sign y1 and y2. Now you just get the initial graph. Now if I take a look, I'm somewhere right around -3. Somewhere right around -3. So let's type in, okay, let's quit off of this. And let's take -3 and store to x. That's my first value. Now we're going to do this one more time. We're going to evaluate at -3. So let's take our y bars, option 3, at x. Let's store to x. Second enter, pulls down my y3 at x again. -3.489. I store this to x. Second enter. I get 89734. Here I have 852. I store to x. Got to go one more. Second enter. Enter. Now I have it. That's my other value. Newton's method of solving equations is a nice technique. Once again, this is a formula like a quadratic formula that you sort of have within your calculator if you need to utilize it. This here basically, if you ever get into computer science and programming, when you go to college and if you have to do some basic computer programming classes, Newton's method is one of the programs you have to write. It is not a difficult program to write. I remember having to do it when I was in college and had to do some basic programming. That was back in the day where you had these cards that you had to type out a program and have a program. You'd have a stack of 10 or 20 cards that you would have to go to a card reader that would run the cards through and then read the cards and run a program. It was, and if sometimes like with our copy machine, a piece of paper, one of the cards would get stuck or back corner, it would jam it up and there'd be a line of about 15 people waiting for you to, get that unjammed and get it out of the way, and you're holding them up, and, or you mistyped, you didn't put a comma in where you needed to put a comma in. So you ran the program and it didn't work. So you had to find which line did I mess up, retype that card, find that card, replace the card that you messed up, and it was a pain. It was a pain to deal with.
We have to do that in coding right now. Like where if you mess it up, you gotta like go through and it's like, well, this could cause this, and then well, that's not it. And then
Yeah.
it's like a massive process of.
Yeah, it is.
Except the repair isn't as bad as that. Where you
Yeah.
rewrite it and whatnot.
Homework. I guess we're done. Homework's yesterday's homework, 349, 713, 1723. We'll work on this more on Monday too. Then we'll get into anti-derivatives. Adios. I guess the bells are still on. Have a good day. Yeah.
Do you think I can just use it?
Real quick. I tell you, just use it real quick. I understood.
Plus or minus.